So as I am a postdoc in the group of Professor Alisavechi, de Ubeda del Pino, University of Sao Paulo. And the topic that I am going to talk about now is tightly related with magnetic reconnection in the vicinities of black hole, as Professor Alisavechi has already commented. And okay, but in particular, I am focused in the core region of these accretion flows because we found it very interesting. In these regions where the flow is accreting close to the black hole, you can find turbulence, you can find very intense radiation fields, you can find, maybe you can do theoretical studies of particle acceleration, as has been commented by previous talks. And currently there are also numerical techniques that can allow to study complex phenomena in more detail. So analytical studies are very useful to understand and also to have insights of the problems, and numerical techniques as well are important. So this work is more numerical. So the overview of this talk is I'm going to comment some points on what motivates us to study very high energy emission in the core region of black hole systems. Then this work is based in particle acceleration by magnetic reconnection and emission produced by hadronic interactions of these accelerated particles with the environment. I am going to show the kind of environment that we numerically obtain. And then I am going to show some preliminary results that we are obtaining with this setup of techniques. And at the end, I am going to mention the conclusions. So, non-blazar systems, as you know, launch jets that are not pointing in this line of sight. So, if you want to explain very high energy emission from these systems, you cannot easily apply Doppler boosting corrections in order to enhance the frequency of the radiation. Also, observations show variabilities in compact zones. For instance, there are some authors that claims that this variability corresponds to sizes of the order or less than the cross-section of the jet. And as have been mentioned in Fraga talk, there is some troubles when you want to explain with a single zone synchrotron self-emission the very high energy emission of these radio galaxies, Perseus A, IC 310, also Centaurus A. For example, this is a very new observation, upgrade observation of the radio galaxy Centaurus A. And in this HES collaboration, together with Fermi, they try to interpret with one single zone leptonic emission model employing Doppler boosting, but they need to break in two zones the emission process. So in order to explain the very high energy tail to be consistent with the radio. And it should not be the case. Those systems are composed by thin disk, thick disks, large scale jets, and maybe the parts of the spectral linear distribution, these components should be produced in different regions. Especially in the very high energy tail, we can see in this zoom that this trend suggests that this could be produced by another component, not necessarily the leptonic emission. For this, very recently, as you know, multi-messenger observations of this blazar that with high level of confidence has been attributed the production of neutrino and gamma ray flare. At the end, it favored the hadronic scenario, but to interpret emission of neutrino and gamma rays in jets are also challenging. For instance, in very recently work by these authors, they estimate that the radiation field in a jet is not enough to produce neutrinos with hadronic interaction. So they suggest that these neutrinos should be or could be produced more in the base of the launched jet. For instance, they use a radiatively inefficient accretion flow. Okay, I am here. I am going to talk about hadronic emission models, and I want to mention that these hadronic emission models have been previously considered by works of Gustavo Romero, who is present here, also Professor Elizabeth Chigobello Dalpino, and Petropoulou and collaborators have studied Centaurus A with hadronic models. And what I am going to contribute now is similar models, but with fully numerical treatment or more complete, more general, that allows more general treatment of cross sections, of interactions, and we can relax the approximations. So, as Professor Elizabeth has already talked, the mission zone that we are focused, if we want to produce high energy radiation in the core region, we can use the fact that reconnection acceleration of particles has been tested already, and we can trust that this is not only a speculation. This has been proven in several works. So, if ions are accelerated, they interact with the background fields. For instance, the main processes that produce high energy emission are interaction of cosmic rays with radiation field, interaction of cosmic rays with background ions, and they can at the end produce gamma rays, neutrinos, and also leptons. For instance, you see in this cartoon that while in the flight of a cosmic ray, in the interaction with the background fields produce particles, and then this cosmic ray loses energy. But the emission of the radiation, can also interact with the background fields. So, in the case of very high energy emission, these photons are very susceptible to be absorbed by the same radiation field that produced them. So if they are produced by photopion production, they are also be absorbed by the same photon field. So we can not model this emission just by the P-gamma interaction, but we should study the cascading process. So if you are not familiarized with these processes, this cascading process occurs when first you can produce leptons via photon-photon interactions. There are also other processes that can produce these very high energy leptons, and then these leptons cools due to synchrotron radiation, but also these leptons can compromise the background photon field. And the energy of this very high energy emission will be lowered because of these processes. But, okay, what we want to know is if these hadronic processes that can be produced by particle acceleration can really be efficient emitters of very high energy radiation in the core of accretion flows or low luminosity AGNs. For this, as Professor Elizabeth introduced already, we are employing a background, a numerical background, composed by accretion flow modeled by the Harm code. We calculate the radiation field of this accretion flow, and then we study the propagation and emission of hadronic particles that we assume have been already accelerated by magnetic reconnection. To do this, we have to take into account the energy available in the background system, that is basically the magnetic density, but also we have to respect the upper limits of the neutrino observations. I mean, we can set off a very magnetized accretion flow, but the hadronic interaction, especially for neutrinos that do not interact with any other field, can be we can have an excess of neutrinos. So this is the main constraints that we consider in this model. So as I mentioned, we also stay in the fast light approximation, in the sense that we consider the system. Here I show the gas density and the magnetic field density of advection-dominated flow produced with the Harm code. And then we assume that cosmic rays interact in time scales more shorter than the dynamical time scales of the accretion flow. As you see, these accretion flows produce turbulent structures where you can, I don't know if it's possible in this resolution, but you can see magnetic islands where, for instance, in talk of Louis Kadowaki, he identified in these magnetic islands current sheets, and this is, according to the theory of magnetic reconnection, places very likely to accelerate particles. For a first approximation, we inject cosmic rays with a power law and according to the energy given by the magnetic flux in this zone, and we detect the resulting particles, neutrinos, gamma rays, or cosmic rays in this outer boundary. This is 10 to the power of, for instance, this is a scale of the magnetic field in logarithm scale. So you can see in colors. Okay. So in this particular example, is 10 to the power of 3 Gauss in average. You have more intense values in the vicinity of black hole, and it is the case with the distance. So I will show a model that increases the magnetic field. Okay, but this simulation should be, if you want to consider radiation, you should give physical normalization to the gas density and to the magnetic field and to the aerodynamical variables. So to do this, we consider that according to people or authors that support the idea that the scenario of low luminosity accretion flows follows or state that the X-ray emission is produced in the torus, the radio is most dominated by the jets, and there is a ultraviolet contribution in an outer thin disk. We will scale these physical quantities in such a way that the radiation emitted by the torus is consistent with the X-ray radiation. And with this, we should also assignate a temperature ratio, proton to electron ratio temperatures, and we can obtain the photon field of the system in such a way that the leptonic radiation is consistent with the X-ray part. And then, after the interaction that I previously mentioned, we obtain the resulting cascading emission. And what we are interested in is to see if this can reproduce the high energy tail of the spectral energy distribution. In this case, these observed points correspond to the radio galaxies in entire size, as I already said. And I think your question, Professor Gustavo, this is the magnetic field that we have in this simulation. But as you see, you can have more reconnection energy stored in the cosmic rays to increase the normalization of this resulting emission, very high energy emission. And we did, okay, this is the corresponding neutrino flux with the same parameters. So this neutrino comes from the same hadronic processes. And if we want to inject more energy, we consider a more magnetized background profile. For instance, the easiest way is just to evolve more the system, so the gas will be swallowed more by the black hole, and then the magnetic field could be accumulated in this central region. And also you can normalize your radiation in such a way that the magnetic field is higher and enhance the TPT ratio in order to be the electrons less efficient and be consistent with the X-ray radiation. For instance, this is the leptonic profile. And okay, the thing is that if you increase the energy injected in cosmic rays, even consistent with the magnetic reconnection theory, you can have an excess of neutrinos too. And so this is another constraint. This model, or all these models correspond to one source, while these neutrino observations comes from all the sky. So it's not possible that one source can be close to the neutrino upper limits. So we will rely more in models, I don't know, that are one order of magnitude below the neutrino limits for one source. For instance, this model could be, the model in orange could be more consistent than this model in blue. But as you see, there is another trend that above 10 to the power of 13 electron volts, the gamma ray flux increases. And at a first glance, I thought that this was a mistake or something wrong in our numerical setup. But this can be understood if you look at the mean free path of the interactions. For instance, the gamma-gamma absorption, the mean free path here plotted as a function of the energy of the, for instance, the high energy photon, begin to be higher if you, for this particular photon field, if you go beyond 10 to the power 14 electron volts. So this means that photons will be less likely to be absorbed. And perhaps this radiation could be observed by more sensitive instruments like this future CTA telescopes, if this radiation is physical. And okay, in summary, we have considered a numerical setup to study very high energy emission based in hadronic interactions consistent with magnetic reconnection occurring in the vicinities of black hole accretion flows. Yes, okay, leptonic as a target background, but the main contribution to the high energy emission is the hadronic component. The leptonic part comes in the cascading, because those are in electromagnetic interactions, but the origin of this cascading is hadronic. Also, our very high energy profiles can reproduce the observations, but are close to the limits of ICQ, and this is something that we have to refine in the case that we can. Or okay, and what we can see from this kind of model is that this is more self-consistent than one-zone models because we use less free parameters. And this is work in progress where we have to explore more background profiles. For instance, there are more prescriptions of the TP iteration as a function of the spatial domain. We should study in more detail the production of magnetic reconnection in magnetohydrodynamical simulations. And okay, this is something that is coming very soon. Thank you.